Hi, my name is Mariana Ramirez Cervera, and today I will present our differential equations project. I will be guiding you through a case study, the physics and mathematics behind bungee jumping. Bungee jumping is not only a fun activity, it also combines several important concepts in physics: gravity, elasticity, and motion, all of which can be described with differential equations. By building a mathematical model of a jump, we can understand what happens to the jumper from the moment they leap to the moment they bounce back. We're going to divide the problem in two main phases. First, the free fall before the rope stretches, and second, the oscillatory motion once the rope starts pulling back along the way. I will explain the equation and solutions to describe each part and show you how they fit into a complete model of the jump. Before we dive into the math, let's think about what happens during a bungee jump. At the beginning, when the jumper steps off the platform, the rope is slack, so the only force acting is gravity. This is exactly like freefall, motion under constant acceleration. Once the rope stretches to its natural length, things change. The rope behaves like a spring, pulling the jumper upward with a retorting force proportional to how much the rope stretches. At this point, the motion becomes a mix of gravity pulling down and the rope pulling up. The result is oscillatory motion, similar to a spring mass system. So with this in mind, let's go through the mathematical model step by step. In our first equation, we set up the force balance. Newton's second law tells us that force equals mass times acceleration. Here, the force is just a weight, mg, acting downward. When we divide both sides by the mass, acceleration equals g, which we write as the equation we see. This is the starting point. It tells us that in a free fall, the acceleration is constant and directed downwards. Next, we integrate acceleration to find velocity. The integral of minus g with respect to time gives us the equation we can see, which is equal to the derivative of position or velocity. We call this v of t. The constant c1 is the initial velocity v0. Integrating again, we obtain the position function. This is the classic kinematic equation of uniformly accelerated motion, which describes the free fall before the rope stretches. Now we move into the second phase, when the rope starts stretching. At this exact moment, time is reset to 0. The position is at the rope's natural length, and the velocity is the final velocity from phase 1. These are our initial conditions from the spring mass system. Here, two forces act simultaneously, gravity pulling downward and the spring force pulling upward. By Newton's second law, the net force describes the motion of the jumper once the rope stretches. This equation is non-homogeneous because it includes both the oscillatory spring force and the constant force of gravity. To solve it, we separate the solution into two parts, a particular solution for the constant effect of gravity and a homogeneous solution that represents oscillations. The general solution combines sinusoidal functions. It looks like the one on screen. Here, the constant c1 and c2 will be determined by the initial conditions we set earlier. By applying the velocity and position from phase 1 into the general solution, we solve for c1 and c2. This step personalizes the equation to our specific bungee jump instead of keeping it general. Finally, we substitute the values into the equation, obtaining the displacement as a function of the time. This equation describes how the jumper oscillates up and down around a new equilibrium point. The complete model captures both phases, free fall and oscillatory motion, showing the realistic dynamics of bungee jumping. To conclude, let's recap. We model bungee jumping in two phases. In the first phase, the motion is free fall, described by a single kinematic equation under constant gravity. In the second phase, once the rope stretches, the system behaves like a spring-massed oscillator under gravity. This required solving non-homogeneous second-order differential equations. The final solution shows oscillatory motion around the new equilibrium position. This matches what we see in real life. The jumper doesn't stop immediately but bounces up and down until it's coming to rest. By breaking the problem into stages and applying calculus, we are able to translate the thrilling physical experience into precise mathematical